Hello learners, welcome to Education Online program. I'm teacher Willa Lucia. In our last lesson, we talked about capillary action. Capillary. So we say that when a narrow tube is being dipped in a liquid, what happens is that the liquid either rises in the tube or it falls in the tube. That depends on the type of liquid you have used. So we shall define our capillary action as the rise or fall of liquid in a narrow space due to intermolecular forces between the liquid or the surrounding area. So if we have it like that, we can also demonstrate that. You can try to find out how this action is it. Well, we can get a narrow tube, of different diameters. Or we can also get we can have two different types of liquids. It can either be, let's take mercury and water. So what happens is you get your tubes and dip them in a basin containing water. So when you dip this tube, so this, we expect this to be water, and then we have our tubes here of different diameters. So we are saying the liquid will either rise or fall in a tube. So when we have our liquid like that and our tubes already dipped in this liquid, we shall observe that there would be rise, because this is water. The liquid here is going to rise in these tubes, and they are not going to rise they won't be having the same height, or the liquid column in each of the tube won't be the same. So you see that with this narrow tube, the liquid column is kind of higher than the second one, which is having a smaller diameter than the last one. This is because of the intermolecular forces of attraction between the liquid and the tube. These molecules keep themselves very close to the tube. That's why you see that this one, it rises very high in the narrow tube, because these molecules have been attached together. They bring themselves closer because the space here is small than these other tubes. That is with a case of water. What of the fall? The fall, we can use any other liquid like mercury. So if we have our mercury here, we have a basin of mercury. We know that we're going to dip our tubes also inside. These tubes, they should be the same tubes you used here. You just remove them from there, dry them up, and try to fix in a different, dipping it in a different liquid. So this time, if we have it like that, we said the meniscus of mercury is it curves from the outside, or more like a convex, with a convex shape. So you see that when it is like this in a mercury, instead of this liquid rising up, it is going to fall. There will be fall below the liquid, the mercury meniscus, and the fall in the narrowest, this time is going to be the opposite with that, with the water. This one will be having very less then the rise here will be much greater than the one in the narrowest tube, and the one with the biggest diameter will have a greater fall there. So you'll see that the molecules here, the intermolecular forces between particles in mercury are much stronger than the molecular forces between the mercury particles and the molecules of the glass tube. So all this we saw it in our previous lesson. Today let us see this, how to demonstrate capillary action using chalk brick. Some of us will be wondering what chalk brick is. So chalk brick is just this normal piece of chalk, the one we use when you're writing on a black board. So let's see this demonstration. Demonstration of capillary action using chalk brick. How would you demonstrate capillary action using this chalk brick? What we are going to do is, we shall get you can get 2 chalk bricks. We can have a waxed paper. We need a shallow tray, and then capillary tubes. Those are the apparatus we need for our demonstration. So you will need a capillary tube. We need chalk brick, 2 pieces at least, 2 chalk brick. We need a tray. Okay. So what do we need again? Let's have some colored water. And a waxed paper. So if we have all these apparatus, let's see how we can demonstrate capillary action using the chalk brick. So what we are going to do is, we're going to pour this colored water. The first step is, we get our colored water and pour it in the tray. So let's get we have a simple diagram here. We can have our tray. Then we pour this colored water in the tray. So this one is going to be the tray. This one is going to be our colored water. So if you already have your colored water, what do you do next? We get 1 chalk brick. So we can get this chalk brick, we insert it, let it at least submerge this liquid here in the tray, submerge the chalk brick. So we're going to get it here, we fix it, we dip it in the liquid that is in the tray. So we keep, okay, let it be at least up to that level, so that it can be seen. It enters almost halfway. The chalk brick is almost halfway in the liquid. So what happens is, if you put this liquid like that, you'll see that this water, the colored water, will be moving upwards. So it will be moving from the point where the liquid stops. You'll see that it continues up there. Let's reduce that level somewhere here. So this is our chalk brick. So this liquid you've seen, this is where the meniscus ends. But then the chalk brick will absorb this water, and it will continue moving towards the end, which is not in the water. So what happens is, you get the second chalk brick, and put it right on top of this one. Let's keep it right here. Let them be in direct contact with each other, like that. Okay, let me use another color of that, so that we know that the first one, those are two different chalk bricks. So we are going to have the second one right here on top. So this is our first chalk brick and this one is our second chalk brick. So what you will see is that this liquid will move from its meniscus, leaving the part that has been submerged in the liquid, to this other part that is left empty, and then it moves up to the second chalk brick you've put in the liquid. Why is that? This is because our chalk brick here has it is porous. It has some tiny pores in it. So these tiny pores are first filled with air. So when you put it in water, it is going to absorb the water, meaning that the air inside is going to be displaced. So it will displace the air. It is going to fill itself with the liquid. So the liquid continues to move up using this capillary action, because we say it can either rise, capillary action, or fall. But since this is water, you see that it keeps on rising from here up to the next chalk brick. Now you look at this situation. We are still, remember, we have not used our waxed paper. Then here we are going to have another tray. So when we have that, we can use this tray again here, filling it again with this colored liquid. So when you fill it with the colored liquid, get the first chalk brick, submerge it also, just the same way you did in the first situation there. So we are going to have this, we're going to submerge our chalk brick right here in the liquid. So when you submerge it like that, this time round, get your waxed paper. If you get your waxed paper, put it right on top of this first chalk brick here. This is our waxed paper. Let's have it like that. So now we have the waxed paper. And then we have, this is still our tray, and this is still the colored water. How do you get the waxed paper? To get a waxed paper, you don't need to go to the market and buying it, but you can create your own. You just get a piece of paper, you get grease, any oil, try to smear it, dry it all over the paper. So when you smear it, you leave it, it becomes a waxed paper. So this is how we get our waxed paper locally. So this time round, after putting your waxed paper, now get the second chalk brick. Put it right above this first one here. And observe what happens. In our first situation, we never had the waxed paper, and we saw that the liquid was in position to find its way through these tiny pores from this first chalk brick up to the second chalk brick. But in this case, you see that our liquid is going to move. It will rise right here up to where the wax is, and then you see that our second chalk brick doesn't have the liquid. Why? Even though we say that it is having tiny pores. This is because this waxed paper here and the liquid molecules, the wax paper has got small particles, those molecules also. Instead of this one attracting its molecules with the molecules in water, we find that the forces of attraction between these two between the liquid water and the wax paper is very small. It is very weak. That's why you see that liquid does not pass from this way to the other chalk brick. However much it has the pores. This one here covers up. It blocks the way. It blocks these other pores from the other side. Just because it has very weak intermolecular forces of attraction with water, that means that this one will not, the water doesn't have the ability to move through it to the next porous, to the next piece of chalk. So that is how you can also try that at home to demonstrate the capillary action using the chalk brick. With the colored water, you can get anything, and just as long as you just make the water colored. We are making it colored because we want to observe this liquid actually rising up, because if you just leave it not colored like that, it's going to be hard for you to notice the observations there. So you need something colored. You can use anything to color the liquid. So this capillary actions here, the capillary action is having various applications. Let's look at their applications. Okay. Applications of capillary action. We apply this capillary action in our everyday life, but sometimes we do not know that it is this action. It is the action of capillarity. So one of it can be the spreading of ink. We can have it here as spreading of ink. Or now we can say blotting paper. This blotting paper is when you get a paper, try to wet that paper up. So when you wet the paper, get a drop of ink. So when you get a drop of ink, just drop it right on the paper. Leave it there for some time, and then you come back and observe. You'll see that this ink, the drop of ink you had, if this was your paper, then you had a drop of ink just on this point here. When you come back to see the paper, you'll see that the liquid moves. This drop of ink tries to spread all over the paper. So why does it spread like that? This is because of the action of capillarity. It is in position to move. The molecules in this are in position to attract themselves with the molecules of the paper. So as they keep on attracting themselves, they keep moving from one place to another. They knock each other, move from this point. This one will give it to this one will attach itself with another molecule. So you find out that this ink moves from this position to all the surface of the paper. So we can have another one as the kerosene rising. Up a wick of a lamp. So this one here, how is it possible? You have, if you're using this kerosene, this is more like paraffin. So that lamp there, it has a rope which we call as the wick. So when you dip it, okay, when you have that bottle there, the container you're going to use to light the room, you have a rope that you're fixing it. Then you pour your paraffin or the kerosene there. What happens is that instead of the kerosene just remaining and only the part that you've dipped in the kerosene, the part of the wick is what I'm meaning, to absorb the kerosene, you find out that this kerosene has the ability to move from even the parts that are not dipped, from where it is dipped up to up. That's when you find out that when you light up the wick, it's able to give you the light. This is because of the action of capillarity. It allows this whatever the kerosene to move from where it is highly concentrated to the point where it is least concentrated. So we also have another one, which is the towel drying. Towel. When you wash your towel, what happens? You'll see that this towel will keep on drying, not all at the same time, but it starts from a point as it continues moving. So this is because of the action of capillarity. So you'll see that there are very many other applications out there, even though you will not know that it is actually what you're using this capillarity action. Because if you look at this towel drying, how would you know that it is really the application of that? But then if you go into your books and read, obviously you will find that out. So this capillary action has also things it depends on. Let us look at this. Factors affecting capillary action. We have as factors affecting capillary action. So what is the factor that can affect the rise or the fall of liquid in a tube or in space? So let's see this. The rise or fall, that means that we are talking about what will affect the height of the liquid. So we can have the first one here as we have it as the radius. Okay. We have it as radius of the capillary tube. This radius of the capillary tube affects the rise or fall in a way that when the radius of the tube is large, that means that there will be a reduction. The height at which the liquid will move up will be lower. That means this one, the radius, the height is inversely proportional to the radius. So the more you increase the radius, that means that you're reducing the height. Instead of it rising, there will be a fall. So we have another factor, which is the density of the liquid. How heavy or how light is your liquid? This height here is also affected by that. It is inversely proportional to the density of the liquid. That means that the greater the density of the liquid you're going to use to demonstrate capillary action, the lesser the rise. So if you want to increase this height here during your experiment, that means that you have to reduce the density of the liquid, or you don't reduce the density of the liquid, but you use a liquid with a lesser density. We have another factor, which is the surface tension. We have surface tension. This surface tension here is directly proportional to the column, the rise of the liquid in the capillary tube. So that means that when the surface tension is high, there will be increase in the rise or the fall. If the surface tension is less, it also affects this. For it is directly proportional. So that means that when you reduce surface tension, you're also reducing the height to which the liquid would move in the capillary tube. So today we've learned a lot about this capillary action, demonstrating it using chalk brick. We've talked about the applications, which includes spreading of ink, and this spreading of ink in some subjects like chemistry is known as the paper chromatography. It's still the same thing. So we see the kerosene rising, how the towel drying. So we also have the factors affecting them. We should know that it's the radius. That's why you see that in water, the rise is high in the tube that is having a very small radius. But then when it comes back to other liquids like mercury, the fall is also greatest in the narrow tube. So you see that this one, if you look at this, the applications and the effects, you find out that capillary action is actually very important in our daily life. But then it is also, in some other point, you find out that capillary action is disadvantageous. How? Look at a building. When they are building, you see that down there is water down. So your building will have something like this. It will be absorbing, because we say that liquid rises. So if you have your building like this, we assume this is our wall right there. Below here is the soil, and the soil has water. So you see that this building has also pores, tiny pores in the brick. It is going to absorb this water, and it will rise onto the walls of the building, which can weaken the building, and it can easily collapse. That's why you find out that when people are building, the engineers try to fix some polythene here, just up here, to cut the rise, to cut this. So this polythene here acts here as waterproof. So when the capillary action is taking place, it will reach at this point here where there is polythene bag. You see that the forces of attraction between the molecules of the polythene bag and the water is actually very weak than the forces of attraction between the water molecules alone and the polythene bag, the molecules in the polythene bag alone. So this one will prevent this liquid to enter, to continue to the building, weakening the building. So this one strengthened the building. That's why you see that your building is in position to stay for long without collapsing. So with this, today we shall end right here, but we shall continue with more about surface tension in our next lesson. Thanks for attending with me.